So let's do one more of these finite difference schemes for Black-Scholes. We'll go through it explicit and implicit. I know we've seen some of this before, but there's a slight modification that I'd like to try here. So we're starting out with our regular Black-Scholes equation, and we're replacing the partial derivatives like we do. The v sub s gets replaced with the center approximation. Now I'm doing the same setup here where the ds is like the h, the step size, how I'm chopping up the stocks, whether I'm, like 50 cents, so you're listing the stocks at $1, $1.50, $2, $2.50, etc. That's the h. The dt is how I'm chopping up time. Now, because of the way that the program I'm using, I'm going to replace the dt with just a t here. So this t means the time step. And take a look how I'm splitting up the v sub t. This was always the one that was the different when we did explicit versus implicit. So what I'm doing here is everything is t plus 1 except for this x here, except for this piece. So that means all of our knowns are t plus 1, and our backwards is our unknown here at x. So that means this one is set up for an explicit. But what's different here is when I replace all these pieces, what's different is I'm keeping this v that was on its own. I think up in the notes before we were making that as just a v, so or a b then we were evaluating that also as a known. Now I'm making it as as one of the unknowns, so I'm making it the same as this other x, so that's the same v as that. And let's see what sort of modification, what that does. Just like before, then I'm replacing the a and the b and the c in the way that we did it before, so that we can get something that's computationally straightforward. And when we clean this up, we're going to solve for x, but now it's not just this x, it's also this x. That's our step from here to here. I'm solving for x, and we're getting x is equal some bracket times a, some bracket times b, some bracket, which is hard to see, times c. So I'm going to make this a little bit smaller to try and fit all that in. So these are the brackets, the things that are multiplied by the a and the b and the c. Now, what we'll notice here is that the brackets are made up of, they're not constant, they have s's in them. So for every row of the spreadsheet, if we're doing this with the spreadsheet, for every row of the spreadsheet is a different stock price. So these brackets will be different for every row. The h, that's how we're chopping up the stock, that's a constant. The t, that's how we're chopping up time, that's a constant. The r, risk-free rate of return, that's a constant. The sigma, that's the volatility of the stock, that's a constant. So when we choose all of our values, these brackets should collapse down into, they'll have an s in them. An s and an s squared. The middle bracket just has an s squared, and the other bracket an s and an s squared. So here we are. I tidied this up a little bit here. So the step from here to here is just algebraic tidying. Now, as you're watching this on the video, I guess you can pause it and check and make sure that all my steps are okay for how I was cleaning that up. Now, this is the explicit solution, the explicit equation that I could use to calculate the next. I've got my payoff. I can calculate the next row over using this explicit solution, and plus the boundaries. We know how to do that. What I'm interested now then is to think about like, what's the expected stock price? Well, if I think of these as probabilities, then remember that this A is if the stock goes up in the time step. This B is this A is if the stock drops down in value. It's up in the spreadsheet, but that's because we start labeling from S equals 0, S equals H, S equals 2H, S equals 3H. So this would be if the stock went down in value during the next time step. B would be if the stock stayed the same during the time step. And C would be if the stock went up during that last time step. So then if I think of these as probabilities, as these brackets as probabilities, and you'll notice here I factored out that 1 over 1 plus RT, but that's like RDT, right? So this is our discount factor. We're discounting this future value. So essentially, we're looking at a discounted weighted average of all the values, A and B and C. It's a discounted weighted average. So I'm looking for what's the expected value of the stock. So if the stock goes up, then it goes to S plus H. If it stays the same, then it's S. If it drops down, that's an A, it drops down to S minus H, because that's how we're chopping up the stocks. So if I get the expected value of the stock, then this simplifies to S plus S times RT, or let's clean that up a little bit. Let's factor out that S, because that's going to make it so basically the stock then just grows. The expected value of the stock going through one time step is just take that value of the stock and multiply it by 1 plus R dt. I'll put the dt in there. So basically our stock is not growing, or it's just increasing in value by the time value of money. Let's show then that the weights, now these are our weights, and we're saying they're like probabilities, our weights. Let's show that the weights sum to 1 over 1 plus R dt. Basically then I'm taking this equation and I'm making all the A and the B and the C ones, or I'm getting rid of them. And when I clean this up, and you can again pause the video and check this out, or let's just see here. Let's look at the S squareds piece. Here I've got an S squared T sigma squared divided by H squared, and here I've got half of that, and here I've got half of that. So a minus a whole one plus 2 halves ones, the S squareds piece cancel out. Look at the other side. The pieces that there's 1 over H squared and H squared. There's the 1. That's this 1 that doesn't, that survives. Here I've got an SRH and a minus SRH. They cancel out. So when we clean this all up, this bracket equals 1, and all we're left with is this 1 over R dt, which is matching our expected stock growth then. What does that mean for us? That it means that we weren't getting that in the explicit. We weren't getting that in the explicit when we were leaving this as a B, right? We were getting something close to, we were getting 1 over 1 minus R dt. But if I switch this to an X, then the proper time value of money discounting factor is there. So maybe this is a better way to discretize. Is the other way wrong? No, because all of these are approximations of what's supposed to be a continuous function. So we can discretize it one way, discretize it another. This at least preserves that factor, that time value of money factor. So maybe that's a good idea. Now, the next thing I want to show then is I want to show the expected want to show the expected. I want to get the variance. So the expected change in the stock. So this delta is not the delta from our, like, how much stock do you short. This is like the change in. I'm using the notation of the book. This is our expected DS. Now, I want to show that our expected DS is equal to RS dt. We sort of already have that, right? Because the expected next stock price is S plus SR dt. So the expected change in stock price is the difference between S and S times 1 plus R dt. So that's the SR dt. That's the expected change in the stock price, which that fits in with our assumption of log normal, that ds is equal to I was about to say mu s dt. Of course, we want to grow it at the risk-free rate of return, so we're growing it at rs dt, and then plus the random part, which was sigma s dx, but the expected value of the dx's were 0 because they could go up or down with equal probability. So this is matching our log normal assumptions. I want to get the variance now. So I'm going to get the variance of the change in the stock. I want to get the variance of the change in the stock by thinking of it as the expected value of delta squared, this delta, minus the expected value of delta squared. So if the stock dropped down, then the delta would have been minus h. It dropped down h. If the stock went up, then it went up by h, so the delta is h. If the stock stayed the same, then its change would be 0. So I'm again using these brackets as if they're probabilities, and getting the expected value of this squared, 0 squared, and h squared. And when we clean that all up, we get s squared sigma squared t. And that means that expected value, the variance is going to be expected value squared, which we have now, minus the expected value squared. And if I square root this, clean this up, and then square root it for standard deviation, I get the standard deviation proportional to the stock, and this is the proportionality constant. Now, I have down here is approximately. That's because I'm going to go dt squared is too small. The exact same dt squared is too small that we did before, but also when you think back to the first course when we were doing, we morphed the binomial distribution into the normal distribution. We did this same thing. We said, oh, that's too small, and the only thing underneath the square root sign was this t sigma squared, which now gives our variance proportional to the stock price, proportional to the volatility, and root dt. Root dt, which is what we wanted, right? Because this would be dx, and quadratic variation, dx squared is dt, so dx is root dt. Everything. So in other words, this is starting to look like a good thing to do, because it's matching our continuous model. Next, we would use the forward and the center and get the implicit scheme. But let's skip this implicit scheme for a minute and look back for our, let's just do a tiny example, a ridiculously small example, but just so we can see everything laid out, and that way you'll be good for the midterm, for the explicit stuff. So I want to price a binary straddle, and by binary straddle I mean something with this payoff. So I get 1 If the stock finishes below 5, I get $1. If it finishes above 6, so if anything in between 5 and 6, I get 0. So I could actually price this, right, using the page 200 formulas. I could do a binary call with E equal to 6 plus a binary put with E equal to 5. I could get the formulas for this. I could price this. But I want to use it as an illustration for this method that we're doing, using a finite difference scheme. So I'm going to pick volatility at 0.5. I'm going to chop the stock up at, now this, when I say it's too small, yeah, because my discretization of the stock is going to be bad, and my discretization of time is going to be bad. We should chop it finer to really see what's going on. But I'm just going to chop the stock up. My H is going to be 1. So I'm going to go, the stocks are going to be 0, $1, $2, $3, $4, $5. I guess I have to go past $6. How much past? I don't know, maybe up to $10. The time left is going to be 8 days. Our time step then is going to be per day. We've got a risk-free rate of return. So here's our formula that we had developed up there for our explicit scheme. And we could take this and just straight plug in the volatility at 0.5, the H equal to 1. This time left thing, that doesn't go in this formula. The risk-free rate of return is 1 over 100. We could put all those pieces in. When I do that, and here I'm using that new way that we made. So that V is the X. The dt is 1 over 252. Where does this, so let's see here. This is the V sub plus. I'm saying if the stock goes up, that was our C. The V was our B, and this was our C here. Where does this 8 come from? Well, the volatility is 0.5, so 0.5 squared is a quarter, divided by 2, that's the 8th that's here. So I've subbed in all the constants in this equation, and I can solve this equation from here to here is just switching to the A, B's, and C's. And here I've got the bracket with A, bracket with B, bracket with C. So you should be able to, this is the almost 1, so that's got some time value of money thing in it. Here is, in this step down here, I removed the A and B and C just to simplify things down to see what I got, and that gave me that should be our time value of money. That should be the 1 over 1 plus RDT, right? A tiny bit of discount. The 252, because we're dividing days up by 252. So this is like the sheet that we're doing, like the homework sheet. Time runs 0, 1, 2, 3 all the way up to 8 days. So this is 8 days. This is the payoff. 1 day left, 2 day left, 3, 4, 5, 6, 7, 8 days left. So I'm counting it as like days left. 8 days left, 7, 6, 5, 4, 3, 2, 1, 0 days left. So this is the payoff here. And I've made the stock 0, 1, 2, 3, 4. At 5 it's 0, and at 6 is 1. So I had to make a decision here, right? Because if you look at the payoff, if I made it 5 is 1 and 6 is 1, then that payoff would all be 1s and nothing would happen. Well, it would be smooth. It would be just straight time value of money. It'd be like you're guaranteed to get $1 8 days in the future. How much is that worth? You would just time value of money $1 backwards 8 days, and you'd be good. But so I took the 5 as a 0, and I took the 6 as a 1 to try and represent that. 1, 2, 3, 4, 5. Yeah. Now, that's a good illustration of the fact that my grid is too small. Right? It would be a much better, like a more accurate example if I would have chopped the H up or the stock into, pennies or something. Then whether or not when I was at $5 exactly, whether. Okay, so my computer ran out of memory, so I had to clean some stuff up. Anyway, the idea being that if we would have cut it finer, we would do a better job. The time running this way, the stock running this way. So we have an 11 by 9 matrix. The 9, because I've got 0, 1, 2, 3, 4, 5, 6, 7, 8 days. The 11 being because I start with 0 all the way up to $10. So the stopping at $10, that's a choice that I made, thinking that that's far enough past the $6. The first thing then I did was put in the boundaries. So if the stock ends up at 0, it stays at 0. So I just took this dollar, discounted it 1 day, 2 days, 3 days, etc. So I can fill in the top. Likewise, if it ever hits $10, it won't necessarily stay at $10, but it probably finishes above 6, so you'll get $1. So I just discounted that dollar all the way through. All that's left to do then is fill in these middle pieces, and that's what my equation here is going to do. So this element would be A bracket times the 1 plus B bracket times the 1 plus C bracket times the 1. Nothing interesting is going to happen in the first step except for these 3 cells, because these 3 cells will involve something that's different from a 1. Okay, so here's I'm trying to do the explicit scheme. I put the payoff. Across the top here are the days left. Here's the stock values. I already filled in the boundaries as discounted. So this is just the cell before it, discounted 1 day. So the interest rate 0.01, I just made 1 over 100, and the DT is 1 over 252, so they're just multiplied together there. So now I need to put in this, so these brackets. So this is going to equal to the A bracket times the A value plus the B bracket times the B value plus the C bracket times the C value. So now I just got to fill in what the A and the B and the C are, and they depend on the stock. So I'm down here. It's S squared. So this value squared times 25 divided by 50402 plus the stock value divided by 50402. Now, I want to lock the stock value. I want to lock the A for the stock value. I want to lock the A for the stock value. And now that's this bracket. Now it's repeated over in the C. So let's just copy this. Control C. So it's repeated over for the C, but it's a minus here. So now I just need to type in the B bracket, which is here. So that's the 25200 divided by 25201 minus 25 times the stock squared divided by 25201, and I just need to lock that A value down, and I think I'm good. Now it's the same value here because I'm just discounting this one. The A and the B and the C are the same. That should all be the case except for things that refer to elements that refer to that 0. So now I can move this back, and let's draw this. This is going to be a nice lead into the next section of the class here. So I'm going to go insert, I'm going to make a graph. And this is supposed to be the value of that binary straddle now with 8 days left till expiry. And it looks a little asymmetrical. Well, that's because I did the payoff a bit asymmetrical here, right? It was 0 at 5 but 1 at 6. So that makes this little asymmetry. And I don't like the way I drew it here. I'm going to get rid of this because I want to make a point here. I'm going to make this a scatter plot. Now the X values are going to be the stock values, and the Y values are going to be the values of that option. So now here's what I thought I was typing in binary straddle. Was I? Yes, I was. So now there's the value of the as dots. But I just changed this chart type, and now it looks better because the other one was just the dots. But it's dishonest because look at this little hump here, right? It's flat, flat, flat. There's like a little hump here. How do I know it's a little hump? That's just Excel like guessing. So I'm gonna go back to change type. Maybe this is a more honest if I just connect them with straight lines. Okay, where am I going with this? We've calculated the value of for the, you know, if someone said, okay, there's 8 days left to go on this binary straddle, and the stock is trading at $4. How much is it worth? I could go and say, oh, that's this point right here. It's worth, you know, 0.945. So that's this point right here. And then if someone said, oh no, it's trading at the stock is at $5, that would be this 17 cents down here. And if someone said the stock was $4.50, this straight line's it's a little bit more honest, because what you'd probably do is try and find some point in between here, like you're taking the average. If someone said the stock was $4.10, you'd want to take this point here more weighted towards the $4 than it is the $5. So what you would really be doing is getting the equation for this line that connects these 2 points and once I found the equation of that line, putting in $4.10 and figuring out what that y value is supposed to be. The next part of this class, function interpolation, is all about how do you get the curve that goes through a bunch of points. Because if I'm being super honest about it, this is what we have. We have these points. We're only imagining that there's a curve that goes through. So how do we get the equation of a function that goes through a bunch of points we have? That's what the function interpolation part will do. So one way is to connect them all with lines. We'll learn a few more sophisticated ways than that. So let's go back and finish up what we're doing here. For our implicit scheme, now that involves going backwards with the matrix. We've done this before. I've set up the scheme here as we would have done with our weights. We need to, so let's what's different about this here is I did make, so the B is the unknown here is the unknown is at time step t plus 1, and all the other stuff is no, other way around. The known is the t plus 1 because we know it at the payoff, and all the other unknowns are one step back. But here I left this as a B and not an X. Why? Well, because when we did this when we set this up last time with the implicit, it did work out nice. Our weights did collapse down into just the proper time value of money. So it seemed to work out better when we were doing an implicit if we left this as a B. Now we think if we're doing an explicit, it's better to leave this one as an X. So here are our weights, and I did show you this with MATLAB before. We have to build that matrix, work our way backwards. So that we did before. Luckily we did that before break.